What if every visitor from the interstellar void was a message, a letter written in dust and light, sent from a place no human has ever been? You see, somewhere out there, beyond the sun's warmth, a traveler called 3I Atlas crossed into our solar system. Astronomers like Frank Niebling and Michael Buchner caught its fleeting portrait, 5 delicate exposures, each 3 minutes long, revealing a strange and mesmerizing sight. 2 glowing anti-tails pointing back toward the sun, and a third jet, a great stream of gas, flowing outward as long as the sun appears in our sky. It was as if the comet were whispering something impossible, something we could almost understand. Avi Loeb called it highly unusual, and perhaps that's an understatement. Because, well, anti-tails aren't supposed to look like that. They shouldn't stretch across millions of kilometers or resist the powerful breath of the solar wind. For that to happen, the outflowing material would have to be denser than sunlight itself, by a factor of 1,000,000. So what could shape such a structure? Is this merely nature at its most extreme, or something guided by deeper, hidden laws we've yet to name? Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple: to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. When the comet known as 3I Atlas first came into view, it appeared as a faint smudge against the deep canvas of the night. At first glance, there was nothing remarkable about it. To most telescopes, it was another icy traveler skimming the outer reaches of the solar system, caught momentarily in the sun's gravity before vanishing again into interstellar space. But then, as the images began to arrive, 5 of them, each a patient 3-minute exposure captured by Frank Niebling and Michael Buchner through twin TEC 140 telescopes paired with ASI 6200 sensors. Something began to shift in the collective mind of those watching. What emerged was not the familiar graceful arc of a comet's tail drifting away from the sun, but a shape that defied expectation. 2 brilliant streams of dust and gas, called anti-tails, seemed to stretch toward the sun itself, while a third, narrower plume extended away from it, cutting across the blackness with the scale of an entire star's diameter. You see, that is not how comets behave. At least, not according to the physics we know. Normally, when sunlight warms a comet's surface, frozen gases sublime, carrying dust outward. The solar wind streams of charged particles flowing from the sun at hundreds of kilometers per second pushes that material into a tail that points away from the sunday. But here, the geometry was inverted. It was as though the comet were pushing against the solar wind, carving its own direction in defiance of the forces that should have shaped it. Avi Loeb, a Harvard astrophysicist known for his curiosity about interstellar visitors, called the sight highly unusual, and, well, that phrase barely begins to capture it. What Niebling and Buchner observed in those pre-dawn hours, between 5:08 and 5:23, Coordinated Universal Time, on the 9th of November, 2025, revealed something breathtaking. The anti-tails of 3I Atlas reached nearly 1,000,000 kilometers in length, longer than the distance between Earth and the Moon's shadow during an eclipse. The main outflow stretched almost 3 times that distance, roughly 2.85 million kilometers, glowing faintly in the sun's reflected light. To the human eye, it would appear as a whisper of silver across the void, but to the instruments, it was an eruption of data, a signal encoded in light and in time. And so, scientists began to ask the question that always follows awe: why? What mechanism could sustain such vast structures without tearing them apart? If the gas and dust were produced by simple sublimation, as with ordinary comets, then their velocity should have been less than half a kilometer per second. At that speed, the solar wind would have blown the material away almost instantly, scattering it into diffuse clouds invisible to any telescope. But that did not happen. The anti-tails of 3I Atlas held their shape, resilient and sharp, as though the material within them possessed a density 1,000,000 times greater than the surrounding solar plasma. Now, think about that for a moment. 1,000,000 times denser than the solar wind. That's not a small anomaly, it's a chasm between what we expect and what we see. In the quiet of observatories and data rooms, astronomers ran models, recalculated light curves, checked for instrumental errors. They searched for natural explanations. Perhaps it was an illusion of perspective, they said, a trick of geometry. Sometimes, when a comet passes between Earth and the Sun, its tail can appear reversed, an anti-tail simply because of the viewing angle. But even then, such features are short-lived, faint, and narrow. The ones on 3I Atlas were immense and stable, like twin rivers of light flowing upstream toward the Sunday. Avi Loeb examined the data and noted that these features were orders of magnitude larger than any halo or jet previously recorded. Earlier in the same year, Hubble had observed a faint glow around the object, no more than a few thousand kilometers wide. Now, only months later, the structures had expanded to several million kilometers. The leap was staggering. To sustain such a system, the comet would have to be expelling material at an extraordinary rate, roughly 50 billion tons each month. That's enough to fill an ocean basin, dissipating silently into space. If that were true, then the nucleus of 3I Atlas could not be a mere fragment of rock and ice. It must be enormous, at least 5 to 10 kilometers across, with a total mass between 30 and 50 billion tons. For comparison, that's larger than any interstellar object we've ever detected, and that, well, deepened the mystery. Because the odds of encountering such a massive interstellar comet in our short window of observation are vanishingly small, less than 0.1%. We saw 1I Oumuamua, a tiny tumbling shard, in 2017. Then, only a few years later, comes this vast, active giant. Statistically, that shouldn't happen. The universe doesn't hand out such coincidences freely. Unless, of course, something else is at play. The question that began to echo in scientific circles wasn't merely about size or shape, it was about origin. Where did this thing come from? The interstellar void between stars is not empty. It's littered with debris, ancient and cold. But to send a Mendevier comet, this large, this energetic, through the narrow corridor of our solar system, at precisely the right inclination, only 5 degrees off the ecliptic, seemed improbably precise. The chance of that alignment occurring naturally, Loeb calculated, was about 2 in 1,000. Combine that with the rarity of its size, and the probability drops to roughly 1 in 100 million. Still, probability is not proof. Scientists have learned to be humble before nature's imagination. Perhaps 3I Atlas is simply an elder of its kind, a remnant of some ancient system, carrying volatile materials that react violently to sunlight. Maybe its crust fractured, allowing gas to vent in jets more focused than any we've seen before. Or perhaps it is a comet unlike any we have yet studied, shaped by unknown processes in the vast dark between stars. Each explanation feels both plausible and insufficient, like pieces of a puzzle that fit but reveal no image. As the days passed and the comet drew nearer to the sun, astronomers around the world joined the effort to track its evolution. Amateur observers compared notes online, their telescopes pointed skyward each clear night. Professionals, from ground-based observatories to orbiting instruments, measured the polarization of light, the rate of rotation, the spectral fingerprints of its gases. The numbers came back strange but consistent. The composition resembled that of known comets, water vapor, carbon dioxide, ammonia, but the relative intensities were skewed. It was as if the mixture itself had been stirred by different rules, by conditions far removed from the sun's domain. You know, there's something quietly moving about that idea. A piece of another star's story, wandering here, shedding its history in the form of light and vapor. Every tail, every jet, every faint reflection is a memory written in molecules. When we look at 3I Atlas, we are not just studying physics. We are witnessing time folded into motion, the echo of creation in transit. And yet, amid the wonder, doubt lingers. Loeb and his colleagues proposed that if the jets of 3I Atlas were not purely natural, if they possessed some form of directed energy, some mechanism that produced thrust rather than mere outflow, then the physics would change dramatically. The required exhaust speed, they estimated, would need to reach several kilometers per second, perhaps even tens of kilometers per second, comparable to the exhaust velocity of ion thrusters designed by humans. That would explain the stability of the tails, the persistence of their shape against the solar wind. It would also imply, though cautiously, a level of precision in emission that natural processes rarely achieve. Of course, such an idea is controversial. Science thrives on skepticism. To suggest an artificial mechanism is not to leap to conclusion, but to expand the field of possibility. For now, all that can be said is that 3I Atlas behaves differently, and difference is where discovery begins. The next step, as Loeb reminded his readers, is not to believe, but to observe. Keep the question open. Let data, not desire, guide the way. And so, telescopes continued to watch. The comet's brightness fluctuated as it neared perihelion, hinting at complex interactions between its core and the solar environment. The antitails shimmered, fading slightly as the viewing geometry shifted, yet still defying easy categorization. Each new image added detail but also deepened the mystery, like peeling back layers of fog to find another mist beneath. If 3I Atlas were a natural comet, its sheer activity would place it among the most powerful ever recorded. If it were something more, well, that more remains undefined. But in either case, it challenges our understanding of how matter behaves under the sun's relentless energy. Perhaps the most remarkable aspect is not the comet itself, but the way it forces us to look again, to question what we think we know about the universe's quiet travelers. And as the comet continued its journey toward the inner solar system, approaching that narrow window when it would pass closest to Earth in December of 2025, the anticipation grew. Astronomers prepared instruments aboard Hubble, the James Webb Space Telescope, even probes like Juno and JUICE, ready to capture the light of this interstellar messenger one final time before it receded back into darkness. For now, though, as its twin antitails shimmered like threads of silver thought against the black sea of space, one truth became clear. Whatever 3I Atlas is, it is teaching us to see differently. Because the story does not end here. In the next part, we'll dive deeper into the physics of these strange structures, into the way sunlight and plasma conspire to shape beauty out of chaos, and how, perhaps, they sometimes betray the whisper of something more deliberate, more astonishing, hiding in the flow of dust and light. To understand what makes 3I Atlas so extraordinary, we first have to return to the fundamentals of what a comet really is. You see, in its simplest form, a comet is an ancient remnant, a frozen archive from the earliest days of planetary formation. Most of them are no larger than a few kilometers across, and they spend eons wandering the cold, outer regions of their home systems. When one of these icy relics drifts too close to its parent star, sunlight begins to do something remarkable. The heat seeps through the outer crust, awakening the frozen gases, water, carbon dioxide, ammonia, and more. These molecules begin to sublimate, to leap straight from ice to vapor, carrying tiny dust grains with them. And suddenly, what was once an invisible speck becomes a shining traveler, crowned by a glowing tail that stretches for millions of kilometers. That, at least, is the simple story. But reality, as always, has layers. The classic cometary tail is not a single stream but two distinct entities. The first is the dust tail, pale and golden, shaped by sunlight itself. Each particle is pushed outward by the pressure of photons, tiny packets of light that act like an invisible wind. The second is the plasma, or ion tail, a ghostly blue ribbon of charged gas sculpted by the solar wind, that constant outpouring of high-speed particles from the sunday. The dust tail curves gently, following the comet's orbital path, while the plasma tail points directly away from the sun, tracing magnetic field lines through the solar system. Together, they create the familiar spectacle we have admired since antiquity, a luminous reminder that light can shape matter, and that even in the cold of space, energy finds ways to dance. When astronomers speak of anti-tails, they usually mean something far more modest. Occasionally, because of perspective, the geometry between Earth, the Sun, and a comet can align in such a way that we see a faint stream appearing to point toward the Sun rather than away from it. It is an illusion, a trick of the eye caused by the projection of dust particles lying along the comet's orbital plane. They are rare, short-lived, and typically no more than a faint wedge, visible only to long-exposure photography. Yet, with 3I Atlas, what we saw was no illusion. Those anti-tails were immense, structured, and luminous. To grasp how strange that is, we need to recall the physics of solar interaction. When a comet nears the Sun, every particle released from its surface is immediately subjected to competing forces. The Sun's gravity tries to hold it close. Radiation pressure pushes it away. The solar wind, moving at roughly 400 kilometers per second, drags ions and dust outward, aligning them into the characteristic tail. Against such forces, the gas emerging from the comet's surface, escaping at perhaps half a kilometer per second, has little power. It cannot move upstream against the solar wind. It can only yield. This is why a normal comet's tail always points away from the Sun, no matter the direction of its motion. Now, imagine trying to form an anti-tail of any significant length under those conditions. For the flow of gas and dust to resist being swept away, it must be incredibly dense, so dense, in fact, that its pressure exceeds that of the solar wind by several orders of magnitude. That is why Avi Loeb's calculation, suggesting a density 1,000,000 times higher than the surrounding plasma, feels so astonishing. It challenges the balance of forces we thought we understood. And yet, before we leap to extraordinary explanations, it's important to appreciate how subtle the natural mechanisms can be. When the Sun's rays strike a comet unevenly, say, because one hemisphere contains volatile-rich patches, the outgassing can form jets. These are localized streams of material that burst from the surface like geysers. As the comet rotates, these jets sweep through space, sometimes creating spiral or fan-shaped structures in the coma. If the viewing angle happens to line up with this geometry, the overlapping plumes can project into space in ways that look, from Earth's perspective, like anti-tails. But again, perspective can only account for so much. The structures observed in 3I Atlas were too vast, too well-defined, and too enduring to be dismissed as mere visual quirks. The anti-tails held steady across multiple nights of observation, maintaining their direction even as the comet and Earth changed relative positions. That persistence suggests an actual stream of material, not an illusion of alignment. You might ask then, could 3I Atlas simply be a comet of unusual composition? Perhaps its surface contains ices with lower sublimation temperatures, like carbon monoxide or ammonia, that can erupt violently when warmed. That would indeed amplify the outflow, but it also poses another problem. Such gases would escape at higher velocities, which would make the tails even more susceptible to solar wind deflection, not less. Unless, of course, the outflow were somehow collimated, channeled into narrow jets that reinforce each other, focusing the momentum in a specific direction. Nature, at times, achieves this through topology. Cracks, vents, and pits in the comet's crust can act like nozzles, turning diffuse sublimation into directed plumes. But to create anti-tails that extend millions of kilometers, those nozzles would need to work in concert, aligned with uncanny precision. And that's where the mystery deepens. Because if you could stand close to a comet like 3I Atlas, impossible, of course, but let's imagine you would see the interplay of sunlight and frost as a kind of breathing. Jets ignite, fade, and shift as the nucleus spins. Dust cascades outward like ash from an invisible fire. The entire body becomes a living system of thermodynamics and light. Every grain that leaves the surface carries angular momentum, altering the comet's rotation in small, measurable ways. These changes can tell us about the strength and direction of the outgassing. In the case of 3I Atlas, the variations were minimal. That in itself is puzzling. A comet losing tens of billions of tons of material should be tumbling, spinning faster or slower. Yet 3I Atlas remained stable, as if the forces acting upon it were balanced in a way we rarely see. There is beauty in that symmetry, but also strangeness. It's as though the comet understood its own equilibrium, maintaining just the right configuration to preserve its form while shedding vast quantities of mass. That's what caught Loeb's attention, not the aesthetic, but the precision. Because in physics, stability amid energy flow often points to a hidden mechanism, a feedback loop that regulates output. Nature can do this, of course. Stars regulate fusion through pressure and temperature balance. Planets maintain atmospheres through dynamic equilibrium. But comets are not known for such refinement. They are crude, chaotic, and transient. As the data poured in, astronomers began to revisit models of tail formation. They simulated dust particle dynamics, plasma interactions, and the effects of electric fields induced by solar radiation. One idea suggested that large, heavy dust grains, too massive to be swept away quickly, might linger near the comet's orbital plane, forming what appears to be a backward-pointing fan. Another proposed that magnetic reconnection events in the solar wind could have momentarily altered the direction of ion flow, creating temporary structures that mimic anti-tails. Yet these models struggled to reproduce the scale and longevity observed in 3I Atlas. Perhaps, then, the explanation lies not only in the comet, but in the sun itself. The sun is not a steady beacon. It is a storm of plasma and magnetism. Its wind fluctuates, twisting through space in spirals shaped by rotation and magnetic fields. When a comet moves through regions of differing solar wind pressure, its tails can ripple, fragment, or even reverse locally. What we saw with 3I Atlas could be the consequence of such a crossing, a meeting between an interstellar body and a turbulent patch of solar weather. In that sense, the comet may not be strange at all. We may simply have caught it in a rare cosmic conversation between star and traveler. Still, even this natural explanation leaves a whisper of unease, because for the anti-tails to shine as they did, the particles within them must be remarkably uniform. Scattering light evenly across millions of kilometers requires a consistency of size and density that ordinary cometary dust rarely exhibits. In most comets, the distribution is chaotic, large clumps, fine mist, uneven brightness. Yet the images of 3I Atlas show smooth gradients, coherent lines. It's like seeing handwriting where you expected random scratches. Sometimes, when science meets mystery, it's tempting to jump to the extraordinary to imagine purpose, where perhaps there is only pattern. But what makes 3I Atlas so compelling is not the certainty of any conclusion, but the invitation it extends. It invites us to look closer, to test the edges of what we think nature can do. The anti-tails, for all their strangeness, remind us that the universe is still capable of surprise, even in the simple act of sunlight meeting ice. As the comet moves ever closer to its perihelion, the point where it skims nearest the sun, those same forces will intensify. More heat, more gas, more dust, more opportunity for the hidden dynamics to reveal themselves. Observatories around the world prepare to capture that moment, to watch the dance between gravity, radiation, and magnetism play out in real time. And perhaps, as we move into that next stage of observation, into the realm where the solar wind itself becomes a sculptor, we'll begin to see not only how comets like 3I Atlas form their enigmatic structures, but also how the space between star and stone is alive with unseen power. Because what follows next is not just a matter of heat and light, it is a story about the wind of the sun, that invisible tide that sweeps through the solar system, shaping everything it touches and challenging us once more to understand how something so intangible can move worlds. The solar wind, you see, is one of the great invisible architects of our cosmic neighborhood. It flows endlessly outward from the sun, carrying with it the charged whispers of our star's restless heart. To the naked eye, space may appear silent and still, but in truth it is filled with this ceaseless stream of plasma, electrons, and protons, flung across billions of kilometers at speeds that could cross the Earth in less than half an hour. This is not a gentle breeze. It is a river of energy, flowing at roughly 400 kilometers per second, sculpting everything in its path. Planets grow tails, magnetic fields ripple, and the faint dust of comets is swept into luminous banners that stretch across the night. To understand how 3I Atlas could resist such a force is to step into the heart of that storm. Every comet that enters the inner solar system becomes a stage for a cosmic struggle, a contest between the heat of sunlight and the fury of the solar wind. When the icy surface of a comet begins to vaporize, it releases gas and dust that form a tenuous envelope called the coma. Within that glowing haze, particles collide, charge, and drift outward until the solar wind seizes them, shaping them into the familiar tails that always, without exception, stream away from the sunday. The reason is simple. The pressure exerted by the solar wind dwarfs the pressure of the outflowing gas. In the case of an ordinary comet, the gas expands at around half a kilometer per second, while the solar wind barrels past at nearly 1,000 times that speed. It's like trying to blow smoke against a hurricane. And yet, that is precisely what 3I Atlas seems to have done. Its anti-tails, the strange luminous bands pointing back toward the sun, defy this balance. For them to exist, the comet's outflowing material must have been astonishingly dense, perhaps 1,000,000 times denser than the plasma streaming from the sunday. That figure, proposed by Avi Loeb, is staggering. It implies that 3I Atlas was not merely shedding vapor like an ordinary comet, but releasing it in concentrated torrents, in great sculpted flows that refuse to yield to the solar wind's dominance. The physics of such a balance are difficult to imagine. Consider what would happen to a grain of dust leaving the surface of a comet. The sunlight striking it exerts radiation pressure, pushing it gently away from the sunday. The solar wind adds its own shove, a blast of charged particles that can sweep smaller grains aside in moments. For an anti-tail to persist, the dust must not only survive this onslaught but remain, coherent, moving as a collective stream rather than dispersing into chaos. This requires either gravitational binding from the nucleus, which is impossible at such distances, or cohesive forces within the outflow itself. It's as if the dust and gas of 3I Atlas were moving together in a kind of synchronized choreography, defying the randomness of the solar gale. There's a poetic irony here, isn't there? That something so fragile, dust and vapor, can stand its ground against one of the most powerful forces in the solar system. But physics rarely cares for poetry, and so scientists have tried to find the mechanisms that could make this possible. Some have proposed that the anti-tail of 3I Atlas is not truly a stream pointing sunward, but rather a geometrical projection of a dust plane lying along the comet's orbital path. If large particles, too heavy to be influenced by radiation pressure, linger close to this plane, then, when Earth crosses that same plane, it might appear to us as though a tail extends toward the sunday. Yet this explanation falters under the scale of what was observed. The anti-tail of 3I Atlas was vast, millions of kilometers long, and far too bright to be composed solely of heavy, slowly drifting dust. So we return to the interplay of forces, the comet's gas outflow versus the solar wind. The solar wind exerts what physicists call dynamic pressure, the momentum carried by its charged particles. At a typical distance near Earth's orbit, that pressure is about 2 nanopascals, a vanishingly small force, yet one that dominates the delicate environments of space. To balance it, the outflow from the comet would have to deliver an equal and opposite pressure, which depends on the density and velocity of the escaping gas. For 3I Atlas to hold its shape, its gas flow would need to be thousands of times stronger than any natural cometary jet yet recorded. And so, astronomers began to imagine what kind of interior could produce such power. Perhaps the nucleus contained pockets of volatile materials under immense pressure, sealed for millions of years, and suddenly unleashed as the comet approached the sunday. Such a release could create explosive jets, localized bursts of gas, capable of punching through the surrounding coma and sending dense plumes sunward. These events are rare, but not impossible. Comets like 29P Schwarzmann-Wachmann have shown similar behavior on a smaller scale, erupting unpredictably with jets of carbon monoxide. Yet even in those cases, the ejected material quickly disperses, subdued by the solar wind. For 3I Atlas, the persistence of its anti-tail suggests a continuous, sustained process rather than a transient explosion. Perhaps, then, the comet's internal structure is key. Imagine a network of vents, aligned by rotation, each releasing material in rhythmic bursts. As the nucleus spins, these vents could reinforce one another, producing a spiral flow that, when projected from our vantage point, appears as a straight, stable line. The balance between the comet's rotation, the direction of sunlight, and the geometry of observation could all conspire to produce what we perceive as a coherent anti-tail. It is a delicate dance, one that nature might choreograph only rarely. But even this hypothesis leaves something unsettled. The energy required to sustain such powerful outflows over time would rapidly erode the nucleus. Loeb's calculations suggest that 3I Atlas was losing on the order of 50 billion tons of material per month. That rate of mass loss would consume smaller comets entirely in a single orbit. Yet 3I Atlas endured, its structure seemingly intact. Either it began as an enormous body, many kilometers across, or its surface replenished itself in some way we do not yet understand. There's another puzzle hidden in the light itself. When astronomers analyzed the polarization and spectral lines of the tail, they found subtle inconsistencies. The emission patterns did not fully match what would be expected from a simple mixture of dust and ionized gas. There were shifts in brightness that hinted at complex interactions, perhaps even electromagnetic effects, where charged particles within the anti-tail respond to the sun's magnetic field. If that were true, then part of the anti-tail's stability could arise not from density alone, but from coupling with those invisible magnetic lines stretching through the solar wind. In essence, the comet may have found a way to anchor its stream to the very field that sought to scatter it. You know, that idea carries a strange kind of beauty. It suggests not defiance but harmony, an object moving with such precision that even the chaos of the solar wind becomes a partner rather than an enemy. In that view, 3I Atlas is not battling the sun's outflow but resonating with it, turning turbulence into structure. The anti-tail, then, becomes a visible manifestation of that resonance, a place where the forces of star and stone find temporary equilibrium. Of course, there are skeptics. Many argue that these interpretations stretch the data too far, that the images can be explained by known cometary processes magnified by perspective. And that may well be true. Science, after all, advances by testing possibilities until only one remains. But what's remarkable is how 3I Atlas compels us to reconsider even the basics, to look again at something as well studied as the solar wind and realize that its interaction with matter is still not fully understood. There's another layer to this mystery: time. The structures we see in a comet's tail are not instantaneous. They are memories, fossilized in light. When we look at 3I Atlas, we are seeing the history of its struggle with the solar wind, preserved across millions of kilometers. The particles near the nucleus may have been released hours ago, while those at the tip of the tail left days or even weeks earlier. The anti-tail, in this sense, is not just a structure but a timeline, a record of changing forces written in dust. If the comet's activity varied, if solar storms altered the wind pressure, these changes would ripple outward through the tail like waves on water. By studying its shape, we can reconstruct the rhythm of those interactions, a dialogue between a frozen visitor and a living star. Perhaps that's what makes this story so profound. The solar wind, once thought of as a mere background current, reveals itself here as a creative force. It shapes not only the plasma tails of comets, but also the very boundaries of planetary atmospheres, the motions of magnetic fields, even the evolution of space weather that touches our own world. To study how it meets resistance in something like 3I Atlas is to learn about ourselves as well, for Earth too lives within that wind, shielded by its magnetic cocoon. In a way, every comet is a test, an experiment. The universe runs over and over, sending small worlds into the sun's breath to see how they endure. And 3I Atlas endures spectacularly. Its defiance is not absolute, rather, it is poised, balanced on the edge of dissolution. It reminds us that the cosmos thrives in states of tension, where forces collide and yet create order. The solar wind and the comet's outflow, locked in their silent contest, generate beauty in the process. It's the same pattern we see in so many scales of the universe, from galaxies shaped by tidal forces to the auroras shimmering on our skies. Everywhere, struggle gives birth to light. As 3I Atlas continues its inward journey, the solar wind will grow stronger, its density rising as it nears the Sunday. The pressure will mount, and if the comet truly possesses the extraordinary density that Loeb proposes, we will soon know it. Instruments aboard the James Webb Space Telescope and Hubble stand ready to capture the coming interaction in exquisite detail. If the anti-tail survives the peak of solar wind pressure, it will rewrite our understanding of how comets behave. If it collapses, scattering into formless haze, we will still have witnessed something never before seen, a glimpse of how far the laws of physics can be stretched before they yield. And yet, as the comet draws closer to its moment of greatest trial, another question begins to stir in the minds of observers. Because beyond the visible struggle of gas and wind lies a deeper mystery. How does a comet of interstellar origin carry such resilience, such structure, into a foreign system? What does that say about the space it came from, the stars that shaped it, the forces that sent it here? That question, I suppose, leads us to the next part of the journey. For to understand the resistance of 3I Atlas, we must understand its body, its mass, its composition, its hidden heart of ice and dust. The solar wind may be the sculptor, but the sculpture itself holds its own secrets, waiting for the light of the sun to reveal for them. If we wish to understand what 3I Atlas truly is, we must begin with something that seems almost too simple: its weight. Mass, after all, is the most honest quantity in the universe. Light can deceive, shapes can mislead, but mass tells you how much of something is really there. And when scientists began to estimate the rate at which 3I Atlas was losing its material, they encountered a number that felt almost mythic: 50 billion tons each month. Imagine that, a mountain dissolving into sunlight, grain by grain, every moment. And yet, despite that vast shedding of matter, the comet's structure persisted. Its nucleus remained stable, its form coherent. To sustain such activity without vanishing entirely, 3I Atlas had to be immense. The calculations began, as they always do, with first principles. When a comet releases gas and dust, the rate of mass loss depends on three things: the surface area of the active region, the velocity of the escaping gas, and its density. From the brightness and extent of the tails, astronomers can backtrack, estimating how much material must have been emitted to create the observed glow. The result, 50 billion tons per month, implied an active surface area far greater than that of an ordinary comet. And because sublimation alone could not explain such intensity, it suggested a deeper source of energy, perhaps buried pockets of volatile ice erupting under thermal stress. Now, if you assume that the comet has a typical bulk density, about 0.5 gram per cubic centimeter, like loosely packed snow, and if you imagine it as roughly spherical, you can work backwards from its apparent endurance. Losing 50 billion tons each month, and yet remaining visibly intact for many months, means its total mass must exceed 30 billion tons, perhaps closer to 50. Translate that into size, and you find a nucleus somewhere between 5 and 10 kilometers across. That might sound small, but in cosmic terms, it is enormous, especially for an interstellar visitor. Most known interstellar objects are either faint specks, like Oumuamua, or small comets barely a kilometer wide. 3I Atlas, then, stands out as a giant among wanderers, a traveler carrying not the dust of one world, but the debris of many. You see, mass does more than define a comet's weight. It shapes its behavior. A heavier nucleus can sustain stronger jets without being spun apart. It has gravity enough to hold onto its coma, to keep the outflowing gas partially bound, creating dense regions near the surface that glow more brightly. This might explain why the anti-tails of 3I Atlas appeared so coherent. The gas leaving the comet may have been caught, momentarily, in the gentle gravity of the nucleus before drifting outward. Each molecule became part of a structure held together not by force but by persistence, a slow choreography of escape. And yet, even that picture struggles to capture the scale of what we're seeing. To lose 50 billion tons a month is to expend a colossal amount of energy. Sublimation alone, the conversion of ice to vapor, requires heat, and the sun's light provides only so much. For the numbers to work, nearly the entire surface of 3I Atlas would need to be active, which is rare. Most comets, especially those that have survived multiple passes near stars, develop crusts, insulating layers of dust and rock that seal away the ices beneath. Only small patches, cracks, or vents remain active. If 3I Atlas is venting over its entire surface, it must be unusually young or freshly exposed. Perhaps it was shattered in a previous encounter, its crust peeled away, revealing untouched ice beneath. Or perhaps it has never felt the warmth of a star before, its ice is pristine since the dawn of its birth in another system. This leads to another layer of intrigue. Because the rate of mass loss directly influences how the comet interacts with solar forces, it can alter its trajectory ever so slightly. The steady expulsion of material acts like a gentle thrust, changing the comet's velocity by tiny amounts. With 3I Atlas losing so much mass, one might expect to see a measurable deviation in its path, a non-gravitational acceleration, as astronomers call it. But so far, no such deviation has been confirmed. The comet moves as if guided purely by gravity. That balance, again, feels almost too perfect. How can something shedding matter so violently remain dynamically calm? The answer may lie in symmetry. If the outgassing occurs evenly across the surface, the resulting thrust cancels out, producing no net acceleration. It's as if the comet breathes in all directions at once, exhaling equally into the void. Still, even a symmetric loss cannot last forever. At the rates observed, 3I Atlas must have lost a significant fraction of its mass by the time it reaches Perihelion, the closest point in its orbit around the Sunday. This moment, expected in November of 2025, will test its resilience. The increased sunlight will push sublimation to its limit, and perhaps only then will we see the nucleus falter or fragment. But if it survives that passage, its endurance will become one of the great riddles of modern astronomy. How can a body so active remain whole in the face of such relentless erosion? To answer that, scientists have looked to the comet's possible internal structure. A nucleus of 5 to 10 kilometers could, in principle, contain multiple layers, a compact core surrounded by a porous mantle. If the outer layers act like a sponge, trapping and releasing gas gradually, they could sustain prolonged outgassing without catastrophic loss. This would make 3I Atlas something like a slow-burning ember, releasing energy over time rather than in violent bursts. But even this model requires fine balance. Too porous, and the gas escapes too quickly. Too dense, and it traps heat, building pressure until the surface fractures. Nature's ability to maintain such equilibrium feels almost deliberate, though of course it is nothing more than the outcome of physics probability playing sculptor across aeons. You know, there's something haunting about that image. A frozen world, the size of a mountain range, slowly unraveling under the gaze of a star it has never known. Each molecule of vapor that leaves its surface carries a memory of its birthplace, perhaps a long-dead sun, perhaps a shattered world orbiting another. By measuring how fast those molecules escape, by tracing the light they scatter, we are, in a sense, listening to the comet's biography written in gas and dust. Now, if the mass estimates are correct, then 3I Atlas is not only large but also statistically improbable. The distribution of comet sizes follows a pattern. Small comets are common, large ones rare. The chance of encountering a giant like this in the brief span of human observation, barely a few decades of interstellar detections, is less than 1 in 1,000. Combined with the peculiar geometry of its orbit, inclined only 5 degrees from the ecliptic, the odds seem even slimmer. It's as if the universe conspired to send this traveler directly into our field of view, carrying with it a lesson we have yet to decipher. There's another consideration hidden in those mass estimates: temperature. The rate of sublimation depends exponentially on temperature, meaning a small increase in solar heating can produce a dramatic rise in gas output. If 3I Atlas possesses pockets of supervolatile ices, such as carbon monoxide or methane, these could begin evaporating far from the sun, driving powerful jets long before ordinary water ice becomes active. This could explain why the comet appeared bright and active even at great distances, months before its closest approach. It also suggests that what we are witnessing is a cascade, a self-reinforcing process where initial heating triggers deeper layers to release energy, amplifying the outflow. Avi Loeb's team has suggested that the consistency of the mass loss rate might hint at some kind of regulatory mechanism. If the comet's interior is stratified layers of different compositions, then, as one layer sublimates, it could temporarily cool the next, slowing the process. In this way, the comet effectively stabilizes itself, neither exploding nor fading too quickly. It is, again, a delicate balance, one that invites the question of how such stability emerges from chaos. And perhaps, when we speak of chaos, we should also remember how little we know of what lies beyond our solar system. 3. I Atlas is only the third confirmed interstellar object. The others, Oumuamua and Borisov, were both anomalies in their own right. One was dry and oddly shaped, the other unusually active and fast. To find a third, with yet another unique profile, suggests that interstellar space is far more diverse than we imagined. Each visitor is not a representative of its kind but a singular voice, telling a different story of formation and loss. The immense mass of 3I Atlas, then, becomes more than a statistic, it becomes a clue. It suggests that somewhere out there, in the dusty outskirts of another star system, conditions exist that can produce comets of extraordinary scale. Perhaps they form in the gravitational shadows of giant planets, where ice can accumulate undisturbed for eons. Perhaps they are remnants of collisions, fragments of once larger bodies flung outward during planetary upheaval. If so, then 3I Atlas carries within it not only the chemistry of another world, but also its history, the silent record of its home system's violence and change. And so, as we look at this enormous traveler shedding 50 billion tons of material each month, we are not merely measuring loss. We are watching the story of a foreign world dissolve into ours. Each wisp of vapor is an emissary from a place we cannot yet imagine. Every photon of light that reflects off its tail carries the fingerprint of that other sun, that other time. Yet the more we learn, the deeper the mystery grows. Because now, having estimated the mass and the staggering rate of decay, we must confront the question of probability. How likely is it that such a massive interstellar comet should appear so soon after Oumuamua, its tiny and enigmatic predecessor? Is it coincidence, or is the universe hinting at a pattern we have yet to see? That question, I suppose, leads us naturally forward. For to understand the rarity of 3I Atlas, to comprehend how such a giant could wander into our skies in the brief window of human attention, we must turn to statistics, to chance, and to the strange arithmetic of cosmic encounters. Chance, you see, is a quiet architect of the universe. It works unseen, balancing improbabilities into patterns that seem almost intentional. And when we speak of 3I Atlas, we are, in a way, speaking of chance taken to its cosmic extreme. To find a comet of such scale, mass, and activity, an object 10 kilometers across, hurtling through our solar system from another star, should be, statistically, an event of near impossibility. The odds, when first computed, were so small that even the most patient astronomers had to pause. Less than 0.1%, they said. That's how likely it would be, under ordinary conditions, to witness a comet of this magnitude entering our observational reach in the brief window since we began to scan the skies carefully for interstellar visitors. And yet, here it is, shimmering in the sunlight, trailing tails that stretch across millions of kilometers, indifferent to our astonishment. This statistical unlikelihood becomes even more striking when we remember what came before. In 2017, we discovered Oumuamua, the first known interstellar object, small and strangely shaped, tumbling like a shard of metal across the void. 2 years later came Borisov, a more conventional but visitor, a true comet, shedding gases and dust as it sped through our system. Both were rare, remarkable, and fleeting. And now, only a few years beyond them, 3I Atlas arrives, larger and brighter than both combined. If you were to imagine these events as random rolls of cosmic dice, the chances of such outcomes repeating in such short succession would be vanishingly small. It would be as though the universe were tossing loaded dice, insisting we pay attention. Astronomers, of course, are cautious by nature. They resist the temptation to read intention into probability. But numbers have their own gravity, and these numbers pull the imagination toward wonder. To estimate how improbable 3I Atlas truly is, researchers turn to what's known as the size distribution function of comets. In essence, it describes how many comets exist of different sizes, the small pebbles vastly outnumbering the giants. For every 10,000 comets a kilometer wide, there may be only a handful 10 kilometers wide. Extend that logic to interstellar space, and you find that the density of such massive travelers should be extraordinarily low. The volume of space one must search to encounter a single 3I Atlas is measured not in light years, but in the vastness between stars. Yet we have found one already. That realization leads to two possible interpretations. Either we are astonishingly lucky catching a cosmic rarity purely by chance, or our understanding of interstellar populations is incomplete. Perhaps the galaxy is richer in such bodies than we thought. Perhaps there are billions of large, ancient comets wandering the interstellar medium, unseen until they wander too close to a star. The trouble with this idea is that it clashes with everything we've observed so far. Our telescopes, sensitive to faint light, should have caught glimpses of such travelers long ago. The sky, instead, remains mostly silent. So maybe it isn't only about abundance, maybe it's about patterns, about why these particular objects, each so different, arrived in such a short span of time. Oumuamua, small and dry. Borisov, ordinary but swift. 3I Atlas, massive and luminous. A trilogy of interstellar visitors, each more extreme than the last. Could there be a connection between them, some shared origin or cosmic corridor guiding them our way? Some astronomers have entertained the thought that the solar system might be passing through a region dense with interstellar debris, a kind of drifting cloud of material ejected from the formation of nearby stars. In such a region, encounters would temporarily spike, explaining the apparent clustering. But for that to hold, the geometry of their approach should reflect a common source. It doesn't. Their trajectories point in different directions, each entering from a unique angle, each story unrelated. Still, the human mind resists coincidence when the pattern feels too elegant. We look at the improbable and ask, why now? Why? Us? Perhaps that's an old instinct, the same one that drove ancient observers to read omens in comets. But unlike them, we now have equations, data, and models. And those models tell us that the appearance of 3I Atlas lies far beyond statistical expectation. Avi Loeb himself once noted that if nature produced interstellar comets randomly, we should have waited centuries before seeing one of such scale. The fact that it appeared within years of Oumuamua suggests either an observational bias we do not yet understand or, more provocatively, that something non-random is shaping these events. Of course, non-random need not mean intentional. It could mean that interstellar space is more dynamic than we imagined, that stars, in their restless evolution, eject material in bursts rather than steady flows. When planetary systems destabilize, when stars age and expand, vast belts of comets can be hurled outward all at once, sending waves of debris across interstellar distances. If we happen to be in the path of one such wave, we might witness a temporary surge of arrivals before the silence resumes. In that case, 3I Atlas would not be an isolated miracle, but part of a celestial migration, a whisper from the galaxy's ongoing creation. It's humbling to think that probability itself might be shaped by deeper cosmic rhythms. What seems like chance from our narrow view could be the inevitable result of cycles far larger than we can perceive. Stars live and die, Worlds collide. Systems breathe in and out over millions of years. And every so often, the byproducts of those events, these icy wanderers, find their way into our skies. From that perspective, perhaps the appearance of 3I Atlas is not so improbable after all. Perhaps it is simply our turn to witness what countless civilizations across time and space might have seen before us, the brief passing of a messenger from the dark between stars. Still, there is something undeniably peculiar about its size. If we plot the distribution of cometary masses on a graph, the curve drops steeply beyond a few kilometers in diameter. Objects like 3I Atlas belong to the far tail of that curve, so rare that even within our own solar system, only a handful exist. Hale-Bopp, for example, one of the most brilliant comets of the 20th century, was about 40 kilometers across. It shone so brightly that it could be seen with the naked eye for months. Yet Hale-Bopp was bound to our Sunday 3I Atlas, by contrast, is unbound, crossing the solar system once before vanishing into interstellar darkness again. The probability of a Hale-Bopp-sized comet entering our skies from another star system at this precise era of human observation approaches 1 in 100 million. It's a staggering number. And yet, the universe has never cared for our sense of odds. If we exist at all, if consciousness itself arose from a particular chemistry on a small blue world, then perhaps the improbable is simply the natural language of creation. Maybe rarity, rather than being exceptional, is the rule. In that light, 3I Atlas becomes not an anomaly, but a reminder that improbable things happen all the time. We are merely too limited in scope to see how often. Still, astronomers are not philosophers, and they seek tangible explanations. One possibility is that our detection technologies have improved to the point that we are simply noticing what has always been there. In the early decades of the 21st century, our sky surveys expanded dramatically. Automated telescopes, equipped with high-sensitivity sensors, began scanning the heavens nightly, covering the entire sky again and again. Before that era, an object like 3I Atlas might have passed unnoticed, its light too faint for the instruments of the past. Now, with digital eyes always watching, the cosmos has nowhere to hide. Perhaps the odds were never as low as we thought. Perhaps the universe has always been alive with these wanderers, waiting only for us to look carefully enough. And yet, even this explanation cannot fully ease the unease, because detection can account for quantity, but not for quality. 3I Atlas is not merely large. It is peculiar in every measurable way. Its tails, its density, its alignment, all of it feels just slightly off, as if nature had taken familiar rules and rewritten them subtly, almost teasingly. To see such a body so soon after Oumuamua's enigma feels like hearing an echo before the sound itself, a prelude to a pattern still forming. If we take the numbers at face value, if we accept that the probability of 2 such anomalies appearing in succession is 1 in millions, then we are left with a fascinating tension. Either our understanding of interstellar object formation is wrong, or we are witnessing a genuine statistical miracle, and perhaps both are true. Science has always advanced through moments like this when data defies expectation, forcing us to rebuild our models of reality. In that sense, improbability becomes not a barrier but a gift, an invitation to deeper understanding. You know, there's an old saying in astronomy: rare things happen all the time if the universe is big enough. And our universe, well, it is big enough. Across billions of stars, each with its own comets, asteroids, and debris fields, the extraordinary becomes inevitable somewhere. The only question is when and where we notice it. And maybe, in this brief epoch of human existence, in this fragile moment of technological awareness, it happens to be here, in our sky. Still, the mind lingers on that feeling of unlikeliness, that subtle whisper that something about 3I Atlas does not fit comfortably within randomness. Some have suggested that its trajectory, its almost planar alignment with the ecliptic, could be a statistical outlier so extreme as to warrant new thinking about how such objects enter our system. Others propose that it might have been influenced by gravitational interactions with giant planets or with the sun itself, its path slightly altered into resonance with ours. Whatever the cause, the odds remain slim, and the intrigue deepens. And perhaps that is the true beauty of it, because improbability, when witnessed, transforms into meaning. Not necessarily cosmic meaning, not destiny or design, but the meaning that comes from encountering something that stretches our understanding of what is possible. The improbability of 3I Atlas becomes a mirror for our curiosity, a reminder that even in an age of data and certainty, wonder survives. As the comet continues its slow arc through the inner solar system, astronomers refine their models, testing each variable, adjusting each probability. Some whisper that this could be the beginning of a new era in interstellar studies, where we no longer see such visitors as accidents, but as part of a greater galactic conversation. If that's true, then 3I Atlas is not an isolated event, but a herald, the first of many yet to come. And that, perhaps, is where our story must go next. For if the appearance of 3I Atlas challenges our sense of probability, then its motion, the geometry of its orbit, its uncanny alignment with the very plane of our own solar system challenges something even deeper. The assumption that such objects wander aimlessly. Maybe, just maybe, its path is trying to tell us something about the larger order of things, about the unseen harmonies that guide even the most distant travelers between the stars. Orbit is destiny. In the quiet mathematics of celestial motion, every object traces a path shaped by the forces that bind it, revealing in its curvature a story older than itself. And when astronomers plotted the path of 3I Atlas, they found something that made them pause. Its orbit, instead of slicing through our solar system at a random angle as interstellar objects normally do, lay almost flat along the plane of the planets, tilted by only about 5 degrees from the ecliptic. That's an alignment so rare that, by chance alone, it should almost never happen. Less than 2 in 1,000 interstellar visitors would cross the sun's neighborhood in such a way. Combine that with the improbable mass and luminosity already discussed, and the odds of both coincidences occurring together fall to roughly 1 in 100 million. You see, the plane of the ecliptic is not arbitrary. It's the invisible sheet on which the solar system was born. All the planets, asteroids, and most comets follow orbits that trace back to this thin, flattened disk of dust that once circled the infant Sunday. Interstellar visitors, by contrast, come from everywhere from the random geometries of the galaxy, their paths oriented without regard to our local architecture. Their orbits should cut steeply across ours, entering from above or below the plane like stones skipping at odd angles across a pond. Yet 3I Atlas moves almost as if it belongs here, sliding gracefully along the same celestial roadway that carries Earth, Mars, and the rest of our planetary kin. Astronomers have spent centuries cataloging the inclinations of comets, and the statistics are clear. Within our solar system, low inclination orbits are common, but among the few known interstellar objects, they are not. Oumuamua, for instance, approached at a sharp angle, diving through the ecliptic like a thrown blade. Borisov came in steeper still. But 3I Atlas? It arrived as if merging into traffic, aligning with the solar plane so precisely that one might imagine it had studied our map before entering. Of course, the universe has no intentions, yet such alignments tug at the imagination. To some, the explanation is simple geometry. If interstellar objects are scattered randomly through space, then over vast time, a few will, by sheer luck, pass close to the ecliptic. After all, improbable doesn't mean impossible, it only means rare. But the conjunction of so many rare traits in one object, its immense mass, its density, its spectacular tails, and now its uncanny alignment invites deeper reflection. Could there be something about the way interstellar objects travel that makes them more likely to intersect with the orbital plane of planetary systems? Perhaps gravitational focusing by the sun plays a role, bending their trajectory slightly as they approach, guiding them toward the dense midplane of our celestial disk. This idea, elegant though it sounds, struggles with the numbers. The sun's gravitational lensing is weak on the scales involved. It can redirect an object's path slightly, but not enough to align it so perfectly with the ecliptic. To achieve that, the object would have had to enter the solar system already traveling along a trajectory that nearly matched our plane. In other words, it came to us pre-aligned, which raises the question, aligned with what? If 3I Atlas originated from a nearby star system, it's conceivable that its parent disk shared a similar orientation to ours. The galaxy, after all, is not entirely chaotic. Many stars in our neighborhood were born from the same molecular clouds, inheriting roughly parallel rotational axes. If 3I Atlas was ejected from such a sibling system, one born from the same cosmic nursery as the Sun, then its alignment might not be coincidence at all, but kinship, a kind of familial resemblance written into motion. That's a beautiful thought, that across light years, two systems share a common tilt, and one small fragment from that ancient family has returned to brush past us again. And yet, the probabilities remain daunting. The Sun formed about 4.5 billion years ago, and its birth cluster dispersed quickly, scattering its siblings across hundreds of light years. For one of those systems to send a comet directly into our plane now, with this precision, stretches the imagination almost to breaking. Avi Loeb and others have calculated that the likelihood of such an event, considering random orientations and spatial distribution, is roughly 1 in 1,000. Combine that with the earlier improbabilities of size and activity, and you reach the extraordinary figure of 1 in 100 million, a cosmic coincidence of the highest order. Of course, science thrives on improbable truths. The alignment of 3I Atlas might yet find a natural explanation hidden in the subtleties of orbital mechanics. Some models suggest that long-range gravitational interactions with the giant planets, especially Jupiter, could have modified its path slightly as it entered the solar system, pulling it closer to the ecliptic. Jupiter, the great conductor of celestial traffic, has reshaped countless cometary orbits, capturing, flinging, and refocusing them with its immense gravity. It's not impossible that the same happened here, the giant planet acting as a kind of cosmic guide, bending an alien traveler into temporary harmony with our planetary rhythm. Still, there's something about the precision that resists easy comfort. Even if Jupiter's pull accounts for part of the tilt, the comet would still need to have entered within a narrow corridor of approach, so narrow that the chance remains vanishingly small. The orbit is not random. It feels choreographed. And yet, who or what could choreograph such a thing but the laws of physics themselves, operating through the indifferent beauty of probability? When scientists plot orbits, they do more than trace paths. They reveal relationships. Each line on the chart is a conversation between gravity and motion, between mass and time. The path of 3I Atlas, looping gracefully through the inner solar system, hints at a dialogue not just with our sun, but with the invisible forces that shaped its journey across interstellar space. To imagine that journey is to imagine epochs. Perhaps it began in the outskirts of a distant star's debris field, nudged free by the slow migration of a giant planet. Perhaps it drifted for millions of years, carrying frozen memories of another sky, before a rare gravitational whisper from a passing star altered its fate, steering it toward us. In that sense, its alignment with the ecliptic might be less coincidence and more culmination, the final step in a chain of accidents so vast it begins to resemble purpose. There is a moment in every great discovery when data gives way to reflection, when numbers turn into narrative. The orbit of 3I Atlas is not just a line of coordinates, it is a bridge between systems, a thread linking the familiar to the foreign. Its near-perfect alignment reminds us that the universe is full of unseen connections, hidden harmonies that our equations only begin to glimpse. Whether born of random chance or cosmic symmetry, this alignment draws us inward, asking a quiet question: how much of what we call coincidence is simply pattern we do not yet perceive? And there's another layer still. The ecliptic is not merely the plane of planets, it's also the stage on which the story of life unfolds. The same alignment that guides worlds also governs the conditions that made Earth possible. The stability of seasons, the balance of light and shadow, the delicate tilt that allows water to flow and atmosphere to breathe. To find an interstellar visitor moving along that same plane is to feel, for a fleeting moment, that we are not isolated accidents but participants in a wider order, one that transcends our star. Of course, science must temper poetry with precision. Loeb's statistical estimate 1 in 100 million reminds us that extraordinary claims require extraordinary evidence. But the role of wonder is not to replace logic, it is to sustain it. The more improbable the observation, the more carefully we must measure, the more rigorously we must test. For now, what we have is data beautiful, perplexing data, and a trail of light across the solar plane that refuses to be ignored. As the comet continues its inward arc, its orbit will evolve. Gravitational interactions, solar radiation, and the subtle pressure of outgassing will nudge its path, altering it by fractions of degrees. Each change will be recorded, each shift scrutinized. By the time it leaves our neighborhood, we will know its orbit more precisely than that of any previous interstellar traveler. And in that precision, perhaps, lies the key not only to where it came from, but to how such alignments occur. You know, when you think about it, orbit is not just a path through space, it's a statement of relationship. Every curve is a declaration of connection, a reminder that no object moves alone. The sun pulls, the planets perturb, and even the distant stars exert their quiet influence. 3. I Atlas, in tracing its shallow arc across our plane, has joined that web of connection, however briefly. It is, for this moment, part of our celestial family, obeying the same gravitational song that binds Earth to its sunrise. But as it passes and begins its long return to the dark, one question will linger. Was its alignment a coincidence? A trick of geometry and timing? Or does it hint at something more? An unseen order to the movement of interstellar wanderers, a resonance between systems separated by light years. Perhaps, as with so many mysteries, the truth lies somewhere in between. A coincidence, yes, but one that invites us to look deeper into the structure of the galaxy itself. And that, I suppose, leads us naturally forward. Because if the orbit of 3I Atlas feels too precise, too graceful to be pure accident, then we must explore what kinds of natural mechanisms could produce such behavior, what processes in the life of comets, in their chemistry and evolution, could shape their motion into forms that seem, at first glance, almost intentional. To make sense of 3I Atlas, to pull it back from the edges of speculation and bring it home to the realm of physics, scientists must return to the old and familiar tools of natural explanation. After all, every mystery begins as an outlier, and nature, patient and infinite in her inventiveness, has always found ways to surprise us without rewriting her laws. So, before imagination strays too far, it is worth asking, what if 3I Atlas is, after all, a natural comet, an extreme, yes, but one still sculpted by the same physical processes that govern all others? What mechanisms, hidden in its chemistry or its history, could produce the extraordinary features we see today? Perhaps, to begin, we must look inward into its ice, its crust, and the subtle language of molecules frozen since the dawn of another star. Ordinary comets, those that call the sun their home, are dominated by water ice, with traces of carbon dioxide, carbon monoxide, methane, and ammonia. These are the volatile breath of the early solar system, the raw materials from which atmospheres and oceans were born. But not all comets are equal. Some are richer in carbon dioxide or ammonia than others, and this composition can dramatically alter their behavior as they near a star. A comet rich in these low-temperature volatiles can begin to awaken far from the sun, outgassing strongly long before water ice even begins to sublimate. Its jets can be more forceful, its tails brighter, its activity prolonged. Suppose, then, that 3I Atlas is such a body, a relic from a colder, more distant birthplace, where the chemistry of its formation favored these hypervolatile compounds. As it entered our solar system, even the faint warmth of sunlight from beyond Jupiter's orbit would have been enough to stir it from slumber, triggering eruptions that sculpted the immense anti-tails we observed. This could explain much of its strange behavior without invoking the extraordinary. But there's a challenge in this model too. For a comet dominated by such fragile ices to survive interstellar travel for millions, perhaps billions, of years is a delicate affair. Cosmic rays, micrometeorite impacts, and the heat of nearby stars should long ago have eroded its surface, sealing its volatiles beneath layers of refractory dust. And yet, 3I Atlas behaves as though those ices remain fresh, as though its memory of cold creation has never faded. That, in turn, suggests another possibility. Perhaps this is not a primordial body at all, but one that has lived and died many times before an ancient comet that has already passed near stars on multiple occasions, its surface reworked by heat and loss. In that scenario, 3I Atlas would not be a pristine traveler, but a survivor, a scarred remnant whose interior reservoirs of gas and dust are trapped beneath a brittle shell. Each encounter with a star would crack that shell anew, venting fresh material into space in explosive jets. The comet's behavior, then, becomes a kind of geological respiration. Inhale the cold between stars, exhale violently in the presence of light. Such an object would carry the marks of age, the collapse of porous layers, the formation of fissures that direct jets in unexpected directions, the uneven rotation of a body slowly reshaped by its own outgassing. If the anti-tails of 3I Atlas are the product of such vents, then their alignment could be the natural result of these evolving fractures, each jet reinforcing the others along a plane of weakness. Over time, the comet could have developed an internal architecture of activity channels and cavities, guiding its eruptions into symmetry. What looks to us like precision could simply be the consequence of endurance. Another avenue of thought points to thermal fatigue, the slow warping of materials exposed to cycles of heat and cold. During its long voyage through interstellar space, the comet would have spent eons frozen in silence, its molecules locked in equilibrium. When it entered our solar system, the sudden rise in temperature would have sent waves of expansion through its structure, creating internal stresses that fractured its crust. In such a state, even a small patch of sublimation could trigger cascading releases of gas, with the energy traveling through those cracks like ripples in ice. If the distribution of these fractures happens to align in a certain way, perhaps along the comet's equator or an ancient rotational fault, it could produce a stable pattern of jets that mimic intention. Nature, you see, has a talent for producing order from chaos, if only for a moment. Then there is the notion of layering stratification that arises from slow accretion during formation. Comets are not monolithic rocks, but agglomerations of dust and ice, built grain by grain from the debris of young planetary systems. As these materials accumulate, their composition can vary, forming alternating strata of density and volatility. When heated, the layers sublimate sequentially, each reacting differently to sunlight. A volatile rich stratum might erupt suddenly, venting material at high velocity, while a denser layer beneath releases gas more gently. The interplay between these reactions can generate complex, sustained jets that shift direction over time. For 3I Atlas, whose mass ensures a long thermal lag between heating and response, these processes could unfold over months, giving rise to the persistent anti-tails we've seen. Some have even proposed that the comet's behavior might be tied to the nature of its spin. If its rotation axis happens to lie almost parallel to the plane of its orbit, then certain regions of its surface would experience prolonged exposure to sunlight, while others remain in shadow. This asymmetry could drive continuous, one-sided outgassing, creating structures that appear to resist solar wind pressure. The 5-degree inclination of its orbit, already uncanny in its precision, may further enhance this effect, channeling the flow of dust along the ecliptic and making its anti-tails more pronounced from our point of view. You know, there's a quiet elegance in imagining that such apparent strangeness could emerge from nothing more than geometry, chemistry, and time. A comet as vast and active as 3I Atlas might not need any extraordinary physics to explain it, only the right combination of circumstances, amplified by scale. Yet even within natural explanations, there are limits that strain credibility. To maintain jets powerful enough to resist the solar wind, to lose 50 billion tons of mass per month without tearing itself apart, To shine so brilliantly at such distance, all of this stretches our models of cometary behavior to their edge. That is why scientists continue to explore hybrid scenarios, blending the known with the possible. Some propose that 3I Atlas might contain pockets of superheated gases, formed by the gradual compression of volatile layers under its own weak gravity. When released, these gases could erupt at speeds far exceeding normal sublimation, briefly achieving the pressure balance necessary to form its immense antitails. Others suggest that magnetic effects within the comet's plasma environment could be amplifying the apparent coherence of its tails. Charged dust particles, moving through the sun's magnetic field, can organize into filaments, creating the illusion of structured flow. Of course, these explanations rely on mechanisms we can model but not yet confirm. To test them, astronomers will need detailed spectroscopic data, measurements of gas composition, and high-resolution imaging from spacecraft or advanced telescopes. The coming months, especially as the comet nears its closest approach to Earth, will offer those opportunities. Instruments like the James Webb Space Telescope and Hubble are poised to capture its spectra, while missions such as Juno and JUICE may record the broader effects of its interaction with the solar wind. Each observation will narrow the field of possibilities, inching us closer to understanding whether 3I Atlas is an extreme example of natural law or a hint of something beyond it. Yet, even as we search for answers, it's worth remembering that nature's capacity for variation is vast. The history of science is filled with phenomena that once seemed impossible until a new layer of understanding revealed their simplicity. Lightning, once divine fire, became electricity. The aurora, once a curtain of spirits, became plasma in motion. Perhaps 3I Atlas is another such threshold, an unfamiliar configuration of familiar forces, misunderstood only because we have not yet seen its like. Still, there is an unease that lingers. For each model that explains one feature of the comet, another remains stubbornly unresolved. The immense scale of its tails, the uniformity of their light, the consistency of its mass loss, each demands fine-tuned conditions that, while possible, seem improbably coincident. It's as though 3I Atlas occupies the narrow borderland where natural law and improbability meet, where the universe reveals not its exceptions but its extremes. Perhaps that is precisely why it matters. Every frontier of knowledge begins with the improbable, the event that should not happen but does. To study such things is not to deny nature's rules, but to test their boundaries. In the luminous trails of 3I Atlas, in the vast jet that spans millions of kilometers, we may be witnessing physics stretched to its limits, revealing nuances of solar interaction, material composition, and thermodynamic balance that no other comet has shown. And maybe that's the point. 3I Atlas doesn't need to be extraordinary in origin to be extraordinary in meaning. Its presence reminds us that the universe still has room for wonder within the ordinary, that even the laws we think we know contain uncharted possibilities. As it moves closer to the sun, its light will intensify, and its mysteries will sharpen. The coming observations will test these natural explanations, whether volatile chemistry, structural layering, or the quiet influence of magnetic fields can truly account for what we see. If they can, we will have expanded our understanding of what comets are capable of. If they cannot, we will be forced to look beyond them, to reconsider the boundaries of what can shape and guide matter across interstellar space. And that, I suppose, leads us toward a deeper comparison still. For there is another traveler that came before another messenger from beyond the sun's dominion, whose behavior defied our models in a different way. To understand 3I Atlas fully, we must set it beside that earlier enigma, Oumuamua, and ask why one shines so brightly with mass and motion while the other passed silently, almost invisibly, through the same cosmic stage. When Oumuamua first appeared in the autumn sky of 2017, it seemed at first to be a simple visitor, a faint point of light sliding silently through the solar system. Yet, as astronomers traced its path, they discovered something deeply unsettling. The object was small, no more than a few hundred meters long, yet it moved in a way that defied gravity alone. After passing near the sun, it accelerated, just slightly but undeniably, as though pushed by some invisible force. And unlike every comet ever seen, it carried no visible tail, no trace of dust or vapor trailing behind it. It was dry, dark, and silent, a traveler of pure momentum. You see, that motion was the beginning of a puzzle that still lingers today. For ordinary comets, acceleration after perihelion comes from sublimation, ice turning into gas and pushing gently against the surface, like a slow, steady thruster. But for Oumuamua, there was no outgassing detected, not in visible light, not in infrared, not even in deep spectral analysis. Yet the acceleration was there, tiny but precise, like a whisper of propulsion from an unseen hand. It was Avi Loeb who first asked the question aloud: what if this was not a natural fragment at all, but something else, perhaps a thin, reflective sheet pushed by sunlight, a relic of technology adrift between the stars? Now, years later, 3I Atlas arrives, a visitor of the opposite kind. Where Oumuamua was silent, Atlas sings. Where one left no trace, the other blazes across the sky with immense tails of dust and gas. One resisted detection, the other floods our instruments with light. And yet, the connection between them is inescapable, for both occupy the same improbable space in our history. Interstellar objects, observed within the brief lifetime of a single generation, each carrying mysteries that test the edges of our scientific imagination. Oumuamua, slender and tumbling, told us that interstellar bodies can be unlike anything we've ever known, shaped not as spheres or boulders, but as elongated shards, more like wafers than worlds. Its surface reflected sunlight with unusual efficiency, suggesting materials unlike ordinary rock or ice. It lacked the infrared signature of dust. Some models proposed that it might be a fragment of nitrogen ice, chipped from a Pluto-like exoplanet. Others suggested a sliver of hydrogen ice, evaporating invisibly into the vacuum. Each explanation, though plausible in isolation, carried its own impossibility. Hydrogen ice could not survive the heat of space. Nitrogen fragments should sublimate long before reaching us. And still, the acceleration remained. 3I Atlas, by contrast, requires no hidden propulsion. It hurls itself forward through the sheer force of sublimation, shedding 50 billion tons of material each month in a luminous storm. But its behavior is no less confounding. The immense density of its anti-tails, the stability of its orbit, the improbability of its alignment, all stretch the fabric of our understanding just as Oumuamua did. Where Oumuamua challenged the absence of evidence, Atlas challenges excess. One is defined by what it lacks, the other by what it gives too freely. Together, they form a symmetry of opposites, a silence and a roar. Perhaps, then, they represent two ends of a spectrum we have yet to understand. Oumuamua, a relic of extreme austerity, may be what remains when a comet has lost everything volatile, stripped bare by eons of interstellar erosion. Atlas could be its complement, a newborn wanderer, still rich in ices, freshly cast from its native system. In that sense, the two are not contradictions but companions, snapshots of the same evolutionary story seen at different times. The first shows us the afterlife of a comet, the second its youth. And yet, the differences run deeper than chemistry. Oumuamua's motion was exquisitely smooth, its acceleration following a pattern that matched sunlight pressure almost perfectly. That precision, too precise, some argued, hinted at artificiality. A natural fragment would spin, crumble, or sputter. A thin sheet might drift like a sail. Loeb's hypothesis of a light sail, a device designed to travel on the radiation of stars, was controversial, even radical. But the physics fit. A sheet only a fraction of a millimeter thick, made of reflective material, could indeed be pushed by sunlight enough to account for Oumuamua's acceleration. It was, perhaps, the first time in modern science that the notion of interstellar technology entered the mainstream of discussion, not as fantasy, but as a question worthy of evidence. Then came Atlas, with its enormous mass and overwhelming activity. If Oumuamua whispered of design, Atlas shouted of power. Some could not help but wonder if the two were in some cosmic dialogue, one inert, one alive, one a message, the other the messenger. But to most scientists, such parallels are poetic, not empirical. The rational view remains. These are natural phenomena, products of different origins and histories, whose coincidence in time is a function of probability and discovery, not intention. And, yet, there's a lingering strangeness in how perfectly they mirror each other's extremes. It's almost as though the universe is testing our ability to interpret its language, offering us two riddles, each crafted from opposite truths. One says, "What moves without force?" The other, "What burns without end?" In both cases, the answer may be the same. Our understanding is still incomplete. Consider their shapes and paths. Oumuamua's orbit was sharply inclined, slicing across the solar system at an angle of more than 30 degrees. Atlas, as we now know, travels within 5 degrees of the ecliptic. One comes in steeply from above, the other glides along the same plane as the planets. Statistically, these two orientations could not be more different. If both are drawn from the same random distribution of interstellar objects, then the odds of encountering such contrasting orbits so close together in time are remarkably low. It's as if the universe were conducting an experiment testing how we respond to difference. Some have speculated that these two objects may even share a distant kinship. Perhaps they emerged from the same galactic region, from a cluster of stars whose systems once interacted gravitationally. In such a scenario, the destruction of planets and comets around one star could fling fragments across the void, some dry, some frozen, each following its own destiny. Over time, these fragments would scatter, wandering for millions of years until one day, by chance, a few cross paths with a young, curious species orbiting a yellow sun. If that is so, then Oumuamua and Atlas are not merely coincidences, but echoes of a single ancient event, a cosmic scattering whose consequences are only now reaching us. But even if their origins are entirely unrelated, their juxtaposition is meaningful. Oumuamua taught us humility. It showed how limited our tools are when faced with fleeting visitors from beyond. By the time we realized its importance, it was already gone too faint, too fast, beyond reach. Atlas gives us a second chance. Its brilliance, its mass, its slow approach all offer time to observe, to measure, to learn. It's as though the universe, having teased us with Oumuamua's enigma, has now granted a more tangible mystery, one that we can actually hold in our instruments. Still, the differences in behavior raise profound questions. Why does one accelerate without gas, while the other releases torrents of it? Why does one arrive dry and tumbling, while the other glows with the vitality of outgassing? If interstellar objects represent a continuum of forms, from rocky fragments to active comets, then we must ask where the boundaries lie. What determines which survive as inert relics and which remain volatile enough to ignite near stars? Perhaps the answer lies in their journeys. An object traveling for eons through the interstellar medium is bathed in cosmic rays that erode its surface, darkening and hardening it into something almost metallic. Oumuamua may have been such a relic, all its ices long gone, its body compressed by time. Atlas, on the other hand, may have been a recent exile, ejected from its home system only a few million years ago, still carrying the freshness of its birth. And yet, even that temporal difference cannot explain the deeper pattern that binds them, the sense that both objects, in their own ways, sit precisely at the limits of what natural law allows. Oumuamua was almost too light, too flat, too reflective. Atlas is almost too heavy, too dense, too luminous. Both seem to occupy the thin line between probability and anomaly. It's as though nature, in her infinite diversity, has chosen to show us the full spectrum of possibility in rapid succession, as if to remind us how narrow our definitions truly are. For Avi Loeb, these coincidences are not merely curiosities but clues. He sees in them a continuum of interstellar engineering, an idea that, while speculative, has driven much debate. If Oumuamua represented a relic of technology, a fragment of a light sail, or a component of some long-lost probe, then Atlas might, in a more generous imagination, represent a related phenomenon, a larger, more dynamic structure capable of sustained activity. Of course, such speculation treads the line between scientific possibility and human longing, and the responsible approach remains grounded in observation. But the parallel, once drawn, is hard to ignore. Both objects behave in ways that mimic, however faintly, the effects of propulsion, one through absence of drag, the other through controlled emission. Yet, even if the notion of design proves false, the comparison has value. It reminds us how science progresses not by shying away from the strange but by confronting it. Oumuamua forced us to re-examine what we mean by natural. Atlas does the same, but from the opposite direction. One expands our idea of silence, the other of sound. Together, they stretch the boundary of what we consider possible in the architecture of celestial bodies. You know, I sometimes wonder if this pairing, these twin messengers, might be part of a larger rhythm in the story of discovery. Perhaps each age of science receives the mysteries it is ready to confront. In the 18th century, it was comets that carried fear and wonder. In the 19th, the canals of Mars. In the 20th, the cosmic microwave background, a whisper from creation itself. And now, in the 21st, perhaps our mysteries arrive not from distant galaxies but from the quiet visitors that cross our own sky, bringing with them the questions that remind us how small, yet how curious we are. As 3I Atlas nears perihelion in late 2025, its light will intensify, and its behavior will either confirm or refute much of what we think we know. Its mass loss, its gas composition, its spectral signature, all will be measured in exquisite detail. And as those measurements accumulate, the comparison with Oumuamua will grow sharper. If Atlas proves to be fully natural, it will anchor our understanding of interstellar objects, showing that even the most extreme can arise without intervention. If it reveals inconsistencies, if its structure or motion betray something more deliberate, then the mystery will deepen, and Oumuamua will no longer stand alone as the anomaly that changed how we look at the sky. Either way, both objects have already accomplished something profound. They have expanded the frontier of curiosity. They have made us look outward again, not as conquerors or explorers, but as listeners, attuned to whispers of matter and light drifting through the void. And so, as we stand beneath the same stars that once guided our ancestors, watching one more interstellar traveler glide through the sunlight, we might ask ourselves, what comes next? For if Oumuamua was the first question, and Atlas the second, then surely there will be a third, a new visitor, carrying its own story, waiting to challenge whatever certainty we have left about how the universe sends its messages across the deep. The idea that a comet could propel itself, that the vast streamers of dust and gas trailing behind it might not merely be a passive consequence of heat, but an active form of thrust sounds, at first, like something out of imagination. And yet, that is precisely what Avi Loeb suggested we should at least be open to considering. His reasoning, cautious yet provocative, was simple. If the flow of gas from 3I Atlas were not random but directed, if it possessed a velocity far higher than sublimation alone could produce, then the object might effectively function as a kind of natural or perhaps even artificial thruster. It's a startling notion, and one that challenges us to examine the difference between mere release and propulsion, between chaos and control. To see why this idea even entered the conversation, we must first understand the physics of motion in space. A comet, under normal circumstances, loses mass through sublimation. As sunlight heats the surface, frozen gases turn to vapor and escape, carrying dust with them. This outflow produces a tiny reaction force, pushing gently against the nucleus. Usually, the effect is negligible, a few centimeters per second of velocity change at most. But in some cases, it can accumulate, subtly altering a comet's orbit over time. What Loeb proposed is that in 3I Atlas, this effect might not be random. The immense anti-tails, their persistence, and their alignment suggest a flow more organized than what we see in typical comets. If those streams were collimated focused like jets, the recoil from their emission could generate meaningful thrust. Now, in a natural context, directed jets are not unheard of. Many comets display localized vents or fissures that channel gas outward in narrow plumes. These plumes can create torque, changing the rotation of the nucleus. But in 3I Atlas, the scale is magnified beyond precedent. To sustain its enormous anti-tails, the outflowing material must be moving faster and in greater quantity than any previously measured. Loeb calculated that to resist the solar wind's drag and maintain structural coherence, the ejected gas would need to travel at speeds of several kilometers per second, perhaps even tens of kilometers per second. That's not mere sublimation, that's propulsion. If that estimate holds, the kinetic energy involved would be extraordinary. The exhaust velocity alone would exceed by a factor of 10 or 100 the speeds typical of cometary jets. To achieve that naturally, one would need a combination of heat, pressure, and structural confinement far beyond what ordinary ices could provide. And that's where the question arises. Could such conditions occur spontaneously, or are we witnessing something guided by deeper physics? Perhaps, even by design? Loeb was careful to draw the distinction between possibility and conclusion. He did not claim that 3I Atlas is artificial. He simply noted that its observed behavior is consistent with what one might expect if a thruster-like mechanism were operating. In physics, consistency is not proof, but it is an invitation. And in this case, the invitation is profound. Because if a comet can behave as a thruster, either through natural processes or by construction, it challenges the way we think about motion in interstellar space. Let's imagine, for a moment, the natural case. Suppose the nucleus of 3I Atlas contains layers of volatile compounds trapped beneath denser crusts. As sunlight penetrates, these pockets could heat unevenly, building pressure until they rupture through narrow channels. The result would be focused eruptions of gas, each releasing energy directionally, much like nozzles. The geometry of these vents, shaped by the comet's rotation and internal fractures, could align in such a way that the outflow becomes steady and organized, forming the vast anti-tails we see. Over time, this would act as a continuous propulsion system, unintended, unguided, but functionally similar to engineered thrust. The physics doesn't care about intent. Force is force, whether born of biology, technology, or thermodynamics. But then comes the alternative, a thought that drifts just beyond comfort. If 3I Atlas is indeed an interstellar object, then its origin lies far beyond our sun, in another system where different conditions, perhaps even intelligent hands, could have shaped it. What if, Loeb speculated, the jets are not accidents of geology but deliberate emissions? In that case, their high velocity and coherence would make perfect sense. A spacecraft, for example, could use controlled venting to steer or decelerate during its passage through the solar system. Even if the source of thrust were weak, the low resistance of interstellar space means small forces can accumulate into significant course corrections over years or decades. That is not to say we are looking at an active craft. It could be a derelict, a remnant, a device whose systems once operated autonomously, and now, after ages of drifting, continue to expel trapped material in predictable ways. In that sense, 3I Atlas could be the cosmic equivalent of a fossilized machine, still functioning at some primitive level long after its purpose has been lost. It's an unsettling but fascinating image, a ghost ship gliding through the dark, its engines sighing softly against the sunlight. You know, perhaps that's what makes this hypothesis so powerful. It doesn't require belief, only openness. The laws of motion are the same, whether they describe a comet or a craft. A jet of gas can be both natural and intentional. The distinction lies not in the physics, but in the context. What we need, then, is evidence. And that's where the numbers guide us back to reality. For the outflow of 3I Atlas to mimic propulsion, its exhaust velocity must indeed reach several kilometers per second. The energy required to produce such jets could come from intense heating of compressed gases deep within its interior. That's not impossible for a natural body. We have seen cryovolcanism on moons like Enceladus, where liquid water mixed with ammonia vents into space through narrow fissures, producing plumes at several kilometers per second. If similar processes can occur on a comet-scale body rich in volatiles, they could generate the high-speed outflows observed. Still, the magnitude here is extreme. The total momentum carried by 3I Atlas's jets, if sustained over months, would be comparable to the output of small chemical thrusters used on spacecraft. In effect, it is performing the same physical act, converting internal energy into directed motion on a vastly larger, grander scale. The difference lies only in intention. We build engines to do what nature sometimes stumbles upon by accident. Loeb drew the parallel explicitly. Imagine a spacecraft powered by the controlled ejection of material, much like an ion thruster. In human technology, ion engines achieve exhaust velocities of 30 to 50 kilometers per second, using electric fields to accelerate ions out of a nozzle. Such systems are extraordinarily efficient, requiring only small amounts of propellant to generate thrust over long durations. If the gas flows of 3I Atlas indeed move within that velocity range, then its natural thruster is operating at efficiencies similar to our most advanced designs. It is as though nature has built its own prototype, demonstrating in dust and ice the same principle that engineers on Earth labor to perfect. Perhaps that's the lesson hidden here, that technology, in the broadest sense, is not unique to intelligence. The universe itself experiments with form and function, exploring every configuration that physics allows. Jets, sails, and radiative propulsion are not inventions, but inevitabilities. Stars, planets, comets, they all obey the same rules, and sometimes, by pure coincidence, those rules produce outcomes that look purposeful. The danger, of course, lies in overreading intention where none exists. But the equal danger lies in refusing to see design when it's truly there. Science must walk the narrow path between skepticism and wonder. If we strip away the language of speculation, what remains is still extraordinary. The jets of 3I Atlas, natural or not, represent one of the most powerful outflows ever observed from a cometary body. The density of the anti-tails, the coherence of their structure, and the sustained rate of emission all point to a mechanism operating near the upper limits of what natural sublimation can achieve. Whether guided by geology, magnetism, or physics beyond our current models, the result is the same: an interstellar object demonstrating a kind of propulsion unlike anything we have witnessed before. And that, I suppose, is why Loeb's analogy resonates. He speaks of technological signatures not as declarations but as frameworks, as ways to ask better questions about the cosmos. If a comet can mimic a thruster, if a plume of gas can resemble an engine's exhaust, then perhaps our search for other civilizations need not rely solely on radio signals or visible structures. Perhaps technology, in its most universal sense, is simply any phenomenon that harnesses energy to shape motion. Under that definition, even a comet becomes a candidate, not for certainty, but for curiosity. You see, the deeper question is not whether 3I Atlas is natural or artificial, but whether such a distinction still holds meaning when the outcomes are identical. A jet is a jet, a sail is a sail. What matters is that energy, guided or spontaneous, can produce complexity that blurs the line between accident and intention. And if the universe can produce such intricate behaviors without intelligence, then perhaps it is, in some deeper way, intelligent itself, an endless engine of self-discovery, forever creating forms that echo our own ingenuity. Of course, this is philosophy wrapped in data. For now, we remain observers, gathering evidence, comparing models, waiting for the next clue. The instruments of 2025, the telescopes aboard Hubble and Webb, the spectrometers on Juno and JUICE, will soon provide measurements that test these ideas. The spectral lines of the comet's emissions, the polarization of its light, the fluctuations in its outgassing, all will tell us whether the flows of 3I Atlas behave like ordinary sublimation or something more controlled. Each new observation will refine our understanding, tightening the boundary between what is possible and what is merely imagined. And if, when all the data is gathered, the comet still defies expectation, if its behavior remains too precise, too efficient, too deliberate, then the question will return, not as speculation but as challenge. What do we call a natural process that behaves as if it were engineered? What name do we give to the universe when it begins to resemble the work of mind? Perhaps the answer lies not in certainty but in approach. We must learn, as Loeb has said, to treat anomalies not as threats to science but as opportunities for it. Every mystery is a test of humility, a reminder that knowledge expands only when we allow the unknown to exist. And so, as 3I Atlas continues to move closer to the sun, its jets blazing brighter, its tails unfurling across millions of kilometers, we find ourselves once again on the threshold between explanation and awe. Whether those streams of light are the breath of a natural wonder or the remnants of something long forgotten, they are teaching us the same lesson, that propulsion, in every form, begins with curiosity. From here, the story deepens. Because if 3I Atlas truly is propelling itself, whether by accident or by ancient design, then what we are witnessing is not merely a comet in motion, but a dialogue between physics and possibility. And to understand that dialogue fully, we must look beyond the object itself to the minds, the methods, and the philosophy of science that allow us to interpret such wonders without losing sight of wonder itself. In science, the rarest and most valuable state of mind is one that stands poised between belief and doubt. It is the place where imagination and discipline coexist, where the urge to explain meets the patience to wait. That is where we find ourselves now, at this strange intersection illuminated by the light of 3I Atlas. Because whether this interstellar traveler turns out to be an ordinary comet pushed to extraordinary limits, or something that transcends the natural, its presence forces us to examine what it truly means to think scientifically in the face of the unknown. You see, the story of 3I Atlas is not merely about gas and dust or orbits and probabilities. It's about how we respond when the universe hands us something that doesn't fit. For centuries, that has been the quiet measure of our progress. When Galileo turned his telescope toward Jupiter and saw its moons, he challenged the order of the heavens. When Newton saw an apple fall, he extended that simple motion into a universal law. Each discovery began with something unexpected, something that resisted explanation within the rules of its time. And each moment demanded the same act of courage we now face, to remain open to the possibility that the world is bigger, stranger, and more intricate than we thought. Avi Loeb's insistence on this openness is often misunderstood. His hypothesis that Oumuamua, or even 3I Atlas, might show signs of artificial behavior is not a declaration of belief, it is an argument against premature certainty. In science, dogma does not only belong to religion, it can grow quietly in the crass comfort of consensus. When we assume that every anomaly must have a familiar explanation, we risk closing the very door that discovery uses to enter. Loeb's point, stripped of controversy, is that every unexplained observation deserves a fair hearing. Not faith, not fantasy, just curiosity, disciplined by evidence. That, after all, is what separates science from speculation. Not the presence of wonder, but the willingness to test it, to ask questions that seem uncomfortable, and to build instruments capable of answering them. In the case of 3I Atlas, those instruments now orbit our own planet, waiting. The James Webb Space Telescope, tuned to the faintest traces of infrared light, will soon examine the composition of its jets. The Hubble, ever watchful, will measure its brightness fluctuations. From these data, we may learn whether its activity truly follows the physics of sublimation or something more directed. Whatever the outcome, the process itself, the act of asking and testing is the essence of science. Perhaps the greater lesson lies not in what 3I Atlas is, but in how we choose to see it. There's a subtle danger in certainty, even when it wears the clothes of skepticism. If we decide too quickly that every strange thing is only an illusion, we risk numbing the very sense of curiosity that drives progress. But the opposite danger is just as real. To let imagination outrun evidence, to replace observation with desire. Between these two cliffs lies a narrow path, and the best scientists have always walked it carefully, curious, cautious, and awake. I sometimes think that this balance, this deliberate suspension between knowing and not knowing, is humanity's finest act of faith. Not faith in any doctrine, but faith in our capacity to learn. Every telescope, every laboratory, every experiment is built upon that trust, that the universe is intelligible, that its mysteries can be approached through reason. But reason itself is a kind of reverence. It demands patience, humility, and an acknowledgement that the unknown is not a void to be feared, but a horizon to be explored. 3I Atlas tests that patience because it sits precisely on that horizon. Its tails defy expectation. Its orbit strains probability. Its luminosity outshines theory. And yet, even now, the only honest response is the same one Galileo offered 400 years ago. It moves. It moves. And so we watch. We calculate, we question, we resist the urge to explain too soon. Because every time we rush to classify the unknown, we risk mistaking our ignorance for knowledge. The scientific community's reaction to Loeb's proposals about interstellar objects reveals, perhaps, as much about us as it does about the universe. Some have dismissed his hypotheses as too bold, too speculative. Others have praised his courage for daring to ask questions that might reshape the boundaries of astrophysics. Both reactions are understandable, and both, in a sense, are necessary. Science thrives on tension, the pull between skepticism and curiosity. But what matters most is that the questions remain alive, that they are neither silenced by ridicule nor trapped by reverence, because progress, you see, does not arise from agreement. It arises from friction, the creative spark that leaps between competing ideas. When Newton and Hooke argued about gravity, when Einstein challenged Newton, when quantum mechanics shattered classical intuition, it was never comfort that moved us forward. It was discomfort. It was the audacity to look at something strange and refuse to look away. And so here we are, looking again at a comet from another star, its strange anatomy unfolding across the solar sky. Each night, telescopes gather photons that have traveled for hours, carrying the record of its behavior. Each data point is a note in the music of uncertainty, a reminder that knowledge is not a possession, but a pursuit. The challenge is not to solve 3I Atlas quickly, but to let it teach us how to see more clearly. In the meantime, Loeb and others advocate for what they call the Galileo Project, a global effort to systematically study unidentified aerial and interstellar phenomena using transparent, scientific methods. The idea is simple yet radical: to take the unknown seriously, to build networks of instruments, open data archives, and algorithms capable of distinguishing noise from signal, coincidence from causality. Not because we expect to find evidence of extraterrestrial intelligence, but because ignoring the unexplained is a betrayal of science itself. That spirit, curious but cautious, should define our approach to 3I Atlas. Whether its jets are natural or not, whether its orbit is coincidence or design, the real test is how we respond to the challenge it presents. Will we cling to old assumptions, fitting new data into familiar boxes, or will we allow those boxes to bend, perhaps even break, to make room for something we have not yet imagined? You see, the universe does not owe us simplicity. Its laws may be elegant, but their expression is often wild. Nature delights in paradox, in edges where one explanation gives way to another. When we encounter those edges, as with Oumuamua, and now with 3I Atlas, we are invited not just to measure but to reflect, to ask what kind of observers we wish to be. The lesson of these interstellar visitors is not merely about what they are, but about who we are becoming in our effort to understand them. And perhaps, as Loeb often reminds his readers, the greatest discoveries in history began not with certainty but with willingness. The willingness to be wrong, to be ridiculed, to be patient. When we laugh too quickly at what seems absurd, we forget how many of our own truths once sounded that way. The Earth moves around the Sunday space is curved. Light behaves as both wave and particle. Once, each of these ideas seemed impossible. Now they are woven into the fabric of knowledge. So perhaps, when we look at 3I Atlas and its improbable beauty, we should remember that disbelief and wonder are not enemies, but partners. To be skeptical is to care enough to ask for proof. To be curious is to care enough to seek it. Science, at its best, lives in that conversation. And if there is one thing this comet has already achieved, it is the revival of that conversation on a global scale. Across observatories and universities, from professional astronomers to amateur skywatchers, people are once again asking the oldest of questions. What else is out there? What are we missing? What might we discover if we dare to look differently? In this sense, 3I Atlas has already fulfilled a purpose, regardless of its nature. It has reminded us that the unknown still exists, that even in an age of data and precision, mystery has not vanished, but only deepened. The more we learn, the more intricate the universe becomes, and that complexity is not a frustration, but a gift. Because within it lies the endless frontier of thought, the promise that we have not yet reached the limits of understanding. Perhaps, in some quiet way, that is the message of this interstellar visitor, to teach us humility, to show us that even after centuries of study, the cosmos still has the power to surprise us. And maybe, too, to remind us that knowledge without wonder is incomplete, that the act of inquiry is as sacred as any answer it may yield. As 3I Atlas continues its journey through our solar system, every observation becomes part of a larger dialogue, not just between scientists and data, but between humanity and the cosmos itself. And in that dialogue, our greatest responsibility is not to rush toward conclusions, but to keep the question alive. Because in keeping it alive, we keep science alive. And that, I suppose, leads us naturally onward. For even as we wrestle with questions of evidence and skepticism, there is another horizon approaching the present moment when all theory must meet observation, when our instruments will finally capture the truth written in the light of this interstellar wanderer. It is there, in that coming encounter, that the story will turn once more from philosophy to measurement, from doubt to discovery. The window of opportunity is opening. For all the speculation and wonder that has surrounded 3I Atlas, the arguments, the models, the doubts, everything now converges on a single fact. The comet is drawing nearer, and with it comes the chance to see, to measure, and perhaps, finally, to understand. In mid-December of 2025, it will pass closest to Earth, its path carrying it into a region of the sky where our most powerful eyes, space telescopes, orbital spectrometers, and deep space probes can watch it unobstructed. For the first time in history, humanity will be able to study an interstellar comet at the height of its activity, with instruments capable of probing its very breath. See, proximity changes everything. When a comet nears the sun, it reveals itself layer by layer. Ices sublimate, gases bloom, and the structure of the coma, the luminous halo surrounding the nucleus, unfolds in exquisite detail. Every molecule released carries the fingerprint of its composition. Every flicker of light betrays the physics of its motion. And now, for 3I Atlas, the tools to read those fingerprints are ready. The James Webb Space Telescope will be among the first to turn its gaze toward this visitor. Its infrared instruments are uniquely suited to detect the spectral lines of volatile gases, water vapor, carbon dioxide, carbon monoxide, ammonia, each glowing faintly in its own wavelength. By comparing the intensities of those lines, astronomers will be able to deduce the relative abundance of these compounds and, from there, infer the temperature and density of the outflowing material. If the jets of Atlas behave like those of a natural comet, their spectra will follow familiar patterns: the ratios of hydrogen to oxygen, the distinct fingerprint of carbon-based molecules, the thermal distribution expected from sunlight-driven sublimation. But if the data show irregularities, unusual excitation states, unexpected emission lines, or temperatures inconsistent with solar heating, then something else may be at work. The Hubble Space Telescope, though older, remains a master of precision imaging. From its orbit above Earth, it will capture the comet's evolving structure with unprecedented clarity. Using filters sensitive to visible and ultraviolet light, it will record the morphology of the tails, their brightness, their curvature, their subtle changes over time. By tracking these variations, scientists can calculate the velocity of the escaping material and the forces acting upon it. If the anti-tails of Atlas remain stable, aligned against the solar wind as they have been, then the data may confirm or deny the extraordinary densities inferred from earlier ground-based observations. Hubble's long baseline of measurement will serve as a bridge between past and present, tying the first images taken months ago to the comet's most luminous moment. Meanwhile, the Juno spacecraft, orbiting Jupiter, and the European mission JUICE, exploring the outer system, will provide a complementary view. Though designed for planetary studies, their instruments can detect shifts in the solar wind's density and magnetic field subtle changes caused by the interaction of that wind with the comet's outflow. If 3I Atlas truly emits material dense enough to resist solar pressure, it will leave an observable signature in the surrounding plasma. Juno's magnetometers may detect ripples in the solar magnetic field, while JUICE's plasma sensors could record disturbances propagating outward from the comet's path. In that sense, these distant spacecraft become part of a grand symphony of observation, their instruments echoing each other across millions of kilometers. And here on Earth, the network of ground-based observatories will fill in the gaps. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, and the new generation of robotic telescopes scanning the southern skies will monitor the comet's brightness curve day by day. Polarimetric instruments will measure the scattering of sunlight off dust grains, revealing their size and composition. High-resolution spectrographs will map the velocities within the jets, capturing the rhythm of their pulsations. Every wavelength of light from the ultraviolet through the visible and into the far infrared will contribute its piece to the puzzle. Perhaps most intriguing will be the measurements of polarization. Light scattered by dust carries within it the memory of geometry, the angles at which it strikes and reflects. By analyzing polarization across different parts of the tail, scientists can infer whether the dust is being expelled randomly or along ordered trajectories. A purely natural coma produces a smooth gradient of polarization, symmetrical around the nucleus. A directed outflow, on the other hand, shows alignment, as though the particles share a preferred orientation. If such alignment is found in 3I Atlas, it could indicate that its jets are not isotropic but collimated, perhaps even controlled by internal structures within the nucleus. All of this will unfold in a matter of weeks. The data will pour in faster than it can be analyzed, each image and spectrum another piece of a story we have only begun to write. And yet, even as these instruments prepare to record the truth, a quiet question lingers. What if, after all this, we still don't understand? What if the comet remains an enigma, its light offering answers that contradict one another? That, too, is part of the adventure. For in science, clarity often emerges not from single revelations, but from the slow accumulation of contradictions that force us to see differently. Still, there is reason to hope that 2025 will mark a turning point. Never before have we approached an interstellar object with such readiness. When Oumuamua passed by, our telescopes were caught off guard, the opportunity gone before we could focus. Borisov, the second visitor, arrived quickly and left just as fast. But now, with Atlas, we stand prepared. The instruments are tuned, the models sharpened, the scientists watchful. This is not just observation, it is encounter. You know, there's something poetic about this moment. A visitor from beyond, arriving just as our species reaches a level of awareness capable of studying it. The timing feels deliberate, though of course it isn't. It's simply the intersection of cosmic motion and human curiosity, a dance of chance and preparedness. But within that coincidence lies something profound. For all our technology and precision, discovery still depends on wonder. We have built machines that can read the faintest light from across the galaxy, yet the impulse that drives us is the same one that guided our ancestors who watched comets with the naked eye. Awe mixed with questions. And those questions are multiplying. If the upcoming observations confirm that 3I Atlas's tails are composed of unusually dense material, then we must ask, what could create such a phenomenon naturally? Could chemical composition alone suffice, or must we consider processes we have not yet modeled? If the jets reveal directional structure, are we seeing the effect of internal rotation, magnetic fields, or something more deliberate? And if, against all expectations, the spectra reveal exotic elements, metals or isotopes, rare in natural comets, what then? Whatever the data reveal, they will reshape our understanding of interstellar objects. If the comet behaves as expected, it will strengthen our models of how material from distant systems evolves under the influence of starlight. If it doesn't, it will expand those models or overturn them. In either case, science wins, for knowledge grows not through confirmation but through surprise. Still, as we prepare for these observations, it's worth remembering that instruments, however powerful, are extensions of human perception. They measure what we instruct them to measure. They see only what we design them to see. The deeper challenge is interpretation to read the light without bending it to our expectations. For in every data set lies a temptation to find the familiar instead of the true. And that, perhaps, is why moments like this matter so much. They remind us that science is not only about discovery but about humility. The humility to admit that the universe is under no obligation to make sense in our terms. When 3I Atlas passes by Earth in December, we will look up and see a faint streak in the sky, a reminder of how small we are and yet how capable of asking immense questions. There's a strange beauty in that image. Telescopes scattered across the world and in orbit, all turning toward the same point of light, their data streams converging across continents. Each photon captured is a message from an object that began its journey long before humanity even existed. And now, those photons end their flight on detectors made of silicon and gold, interpreted by minds that dare to wonder what they mean. As the comet approaches its closest point, there will be a moment brief, perhaps only hours when the data are richest, when every instrument is trained upon it, and the universe seems to pause, watching itself being watched. In that instant, the line between observer and observed blurs. We are not merely studying 3I Atlas. We are part of the same story, bound by gravity and light, by the same physical laws that carry it across the stars. And when it moves away again, fading into the black, the measurements will remain. Numbers, graphs, spectral data, perhaps, but within them the warmth of human effort, the echo of nights spent waiting for photons that might change how we think about everything. This is what science does best. It transforms the distant into the intimate, the unknowable into the measurable. It lets us hold in our minds the impossible scale of things and still find meaning there. In a sense, every observation of 3I Atlas is also an observation of ourselves, of our ability to reach outward, to bridge the abyss between ignorance and insight. As the last light from the comet's passage fades, and the instruments turn their gaze back to the quiet stars, we will begin the slow work of understanding what we have seen. The data will be debated, models refined, arguments raised, and answered. Some will claim confirmation, others contradiction. And through it all, one truth will endure. We are still learning how to listen. And perhaps that listening, this act of attention, is itself the next chapter waiting to unfold. For after the light fades and the data settle, the real discovery begins, not in what 3I Atlas tells us about itself, but in what it reveals about our hunger to know, our refusal to turn away from mystery. And somewhere beyond, another traveler is already on its way, another question written in dust and motion, approaching the quiet blue world that cannot stop asking why.